Hello, my name is Eduard Vorobyov. I'm from the Department of Astrophysics, University of Vienna, and the title of my talk is The Formation of Giant Planets via Disk Gravitational Fragmentation. This slide shows a compilation of exoplanets, semi-major axis versus the planetary mass, and you can see that most of the objects are located inside 10 astronomical units, and their origin can be explained by the co-accretion theory. However, there are some objects that are located at distances much greater than 10 astronomical units, hundreds or even thousands of astronomical units. And we need to invoke other planet formation theories to describe the origin of these objects. And one of these theories is the disk gravitational fragmentation. And this theory tells us if the Q parameter is smaller than about 1.5, then any perturbation given to a disk will grow and the disk will develop a spiral pattern. But this growth will stop because usually the spiral density waves heat up the disk and the instability growth is saturated. However, if the disk cooling time is shorter than the growth time of the instability, the disk fragmentation can occur, and it's usually described by this parameter, the cooling time times the orbital frequency. If it's smaller than a few, then the disk can fragment and form clumps, so-called clumps. And this process naturally occurs at large distances from the star, more than tens of astronomical units. And this slide shows a candidate to disk fragmentation. There is a binary star here in the center, and this clump, it's a proto-brown dwarf. I studied disk fragmentation using the FEOSAD code, which includes the gas and dust hydrodynamics equations. The dust equations are highlighted here specifically. This is small dust, grown dust, and dust interacts with gas via friction, including back reaction of dust on gas. And this equation describes the maximum size of dust grains. So the dust growth is taken into account. It occurs due to collisions, and the maximum size is limited by the fragmentation barrier. And here I show an animation of showing the disk fragmentation in the protoplanetary disk. You see already a few clumps flying around, and the bottom panel shows the mass accretion rate on the star. And let's play it. You can see the clumps orbit the central star. There is one forming here. They randomly interact with each other through gravity, and one of the clumps now is pushed towards the star. It approaches the star and loses most of its envelope, producing a burst here, and then it's completely tidally destroyed. So you saw here a process of interaction and migration of clump towards the star. If we look now at this process in more detail, I plot here the mass of the clump as a function of time. Here is the position of the clump from the star, and here is the temperature in the center of the clump. Then we can identify the four stages of protoplanetary formation here. First, the clump, pure clump, forms at some hundreds of astronomical units and migrates towards the star. Then in the second stage, the temperature inside the clump reaches 2000 Kelvin, and that induces the dissociation of molecular hydrogen, and the center of the clump collapses. However, the atmosphere of the clump, the outer regions, still survive for some time because the clump is rotating. Only the inner parts of the clump are involved in this collapse. However, as the clump comes closer and closer, approaches the star, the tidal truncation occurs. See this the process here, the mass, it reaches a peak mass here, and then the mass of the clump quickly drops. This is the tidal truncation, and the accretion burst occurs here. And in the final stage, the clump is fully disintegrated. However, the core is supposed to survive. the core of the clump, and we calculated the seed core, and its mass is about 1 Jupiter mass. What you saw before was the dynamics of a pure gaseous clump. Now I show a similar case, now including the dynamics of dust. On the left is the gas surface density, on the right is the dust surface density. The size of dust here is about maximum size, about a few millimeters up to a centimeter. And now I plate, you see the clump orbits the star here, and what you can notice that the gaseous clump is much more extended than the dusty clump. This is important. So the dusty clump is quite compact, much smaller than the gaseous clump. And you see other clumps flying around as well. So let's now move further and look at this slide, which is a similar slide as before, showing the masses of the clump, the radial distance, and the central temperature. However, in this case, I show the dust mass and the gas mass. So the gas is the red line, and the dust is the black line. What you see, again, the clump migrates towards the star. The central temperature exceeds 2000 Kelvin, forming the central core. However, what you see here, that the gas mass is gradually decreasing, showing that the clump gaseous atmosphere is completely lost, so it's tidally disintegrated. However, the mass of the dust stays constant during all this process, meaning that the dusty core is very compact. The dust core is very compact. It's not subject to tidal destruction. And finally, we have a protoplanetary core enriched with dust. And the dust to gas mass ratio is a factor of 2 greater than the usual value. This process was, what we saw, this process is known as the tidal downsizing theory. It was put forward by Sergei Nayakshin. We confirmed the main constituent parts of this process here. And the process starts from gravitational fragmentation, formation of the clumps. The clumps interact with each other and migrate inward. And then there are 3 major events that can occur with this migrating clumps. First is the formation of a dusty core inside the clump, then the clump tidal destruction, and H2 dissociation and core collapse of the clump. And depending on the sequence in which these events occur, there are different outcomes. So let's assume that first event 1 occurred and event 2. So first the dusty core forms, and then we have clump tidal truncation. That means we would form a Neptune on Earth-type planet. If only event 2 occurs and there is no dusty core formation, neither H2 dissociation, then the clump destruction occurs, followed by outburst, accretion outburst, luminosity outburst. If event 3 occurs and then event 2, first the H2 dissociation and then formation of a dusty core, then we have a giant planet enriched with a dusty core. So depending on the sequence of these events, we can have different outcomes. And this is the conclusions of my talk. Thank you for attention.